So yes, thanks you guys for stopping out. This talk is going to be about APIs made purely for mobile networks. It's just a completely different paradigm than on the normal web. So I wanted to try and dive into my world a little bit and what I do every day at Listener. So who am I? My name is Chris Ridenour. I had a little stint at P&G. I went to Rockfish Interactive. I was there for about 2 years. And then I left and did my own startup called Listener. So just a quick bit about Listener and why I made some of the decisions I did. We are a mobile-only, push-based content management system. We work primarily in the entertainment industry, and we actually deliver content through high-frequency audio decoding. So what that really means is we create high-frequency sound files, layer them over music or TV or movies, and then your phone can actually decode those and deliver content to your phone. So we started on a bus. It was called the Startup Bus. It left out of Columbus in March of 2012, and it drove around the country for 3 days heading towards Austin, Texas for South by Southwest. The goal was when you reached Austin to actually have a company, a business model, a demo, and pitch it against 100 other companies that were down there. We ended up going to the semifinals, but we bombed it, so we didn't go much farther. But based on that, we realized we had enough interest from people like Pepsi and Disney while we were down there that we should actually make this a real thing. So what are some things that are listener-enabled? We worked with Swedish House Mafia during their last tour. We worked with J. Cole he did a listening party. We're going to do the Made in America Festival this year. And this talk is actually listener-enabled. So if you want to download Listener, it will deliver the slides right to your phone. I might have to lift up my laptop so you can hear the audio. But you can go ahead and download the slides direct to your phone. So let's kind of get into what's wrong with REST, because I kind of bash it in the abstract of this talk. And there's actually nothing wrong with REST as it is. It just doesn't make sense on a mobile. We wrote the first version of Listener using TastyPie and Django, followed all the right things for REST, and found out that it just was the slowest thing you've ever seen because we had so many network requests just to browse through the app because Listener itself was a thin client. It's just reading everything off a server. It's caching it locally, but anytime there's an update, it takes 30, 40 network requests to actually get all the new data. You can mitigate that a little bit, but at the end of the day, REST is very separated, and for good reason. It makes a good API, but when you're on mobile, that doesn't add up. Some of you might say, but I have LTE, why do I care? Well, now Cricket sells the iPhone, so they're not going to keep up with the data speeds of Verizon and AT&T. And even if you have those, they bounce the signal around so much that the latencies are so high that if you have a mobile app, you are going to be sluggish. Just to kind of give you a quick look at where that signal goes. These are all locations of AT&T users in that same IP subnet. And you can see they're just all over the country. And all of them are originating out of one data center, and as it bounces around. So whether you're in California or you're on the East Coast, your signal is going through the same place. So you can't rely on any sort of reasonable latency. The end result of that is mobile networks. I mean, you're lucky with a 400, 500 millisecond latency. Once you make that connection, then you start getting crazy LTE speeds of 30 megabit down and things like that. And obviously, if you're in a major city, it's not as much of a problem. Sometimes you can get down to about 100. But when you're writing a mobile API, you want your app to work as well in the middle. If you're taking 71 from Cincinnati to Columbus, there's nothing in between there. You don't have LTE. You have 3G if you're lucky. So you want that to work just as well there as it does in a big city. And one more reason mobile networks suck. Even if you do have the really, really good really good latency, it's a perfect world. you're still limited to 2 concurrent connections. So if you have a mobile application and you're trying to talk to your API, you can only do 2 things at a time. It goes up to 6 when you're on Wi-Fi, but that's not what this talk's about. So I make a couple of assumptions on my next slides about why you're writing this API or why you're at this talk. The idea is that you're in control of both the API and the client. So you can make changes on both. You're assuming the data does not need to be perfectly real time. So you're not writing a new Snapchat or anything like that. This is data that can be synced up later, can live in a queue, and that this has to be worth it to you. I mean, if this is just an app that needs to download a new blog post once a week or a new podcast, you don't necessarily need to follow this because this is made for apps that are pure online apps. So let's start off with just some easy wins. A lot of these may seem obvious just from writing any API, but they're really, really important in the world of mobile because with that high latency, the only thing you can really do is make it as fast as possible once you're on the server so it can immediately get back and travel that latency all the way back to your phone. The first is pretty obvious. It's just be fast at everything, especially reads. Everything should be cached, whether it's Memcache, Redis, anything like that. Python has amazing support for every one of those libraries, and keeping caching for all of your reads is super important. There's probably very few cases if you're writing a web API that you shouldn't have caching involved, and that's only if you just have tens of thousands of different endpoints that people could access. But even then, it's probably still worth it. A really big one for us is don't make me wait. So when something does actually happen, that the client needs to report back to the server, you should immediately return. You say, okay, thanks, and don't wait for that to process. Put it in a queue. Things like Celery queues are amazing. They take in a request, store it in something like Rabbit or even Redis, and then workers come later and pull them out and actually process them. This is used really heavily in e-commerce transactions. So when you do come under load, rather than making people wait 30 seconds and then timing out, you're immediately just saying, hey, thanks for the request. We'll email you when it's done. In the mobile sense, that's usually, thanks for the request. We'll send you a push notification when we've gotten around to it. So you don't have to worry about big spikes in writes, and you don't have to keep the radio on if there's a slowdown. And the backside of that is avoid sending bad data in the first place. A lot of times people will leave that, they'll wait for their response from the write because they want to make sure everything's okay. They want to make sure that, I didn't send bad data, the server does validation. If you're in control of both the client and the server, the client should be validating everything on mobile before it ever touches the radio, before it ever sends it out. The only times that you should be really validating on the server side is things that need to be unique, things like email addresses and usernames. But everything else should just be avoided on the client side, if at all possible. And this has probably been the number one thing that we've changed on Listener that's had a really good effect, is stay in control. So if you want to connect with Facebook, you want to connect with Twitter, you want to do really anything that involves a third-party API, you should do it through your server and not through the mobile. Because anytime Facebook needs to pull itself or Flurry Analytics needs to send something they did, they're taking up one of those concurrent connections you can have, as well as they're just making your app drain more battery, even though it's outside of your control. By sending everything through your server, you're 100% aware of everything going to and from that application, how much bandwidth it's using, how much battery it's using, and everything you can do on the mobile, you can do better on your server. It's going to be faster, it's going to be around more often, and it's just a much better experience overall for the user. So now for the meat of this presentation, what are the strategies we can implement to minimize that cost of the latency? We're not going to be able to fix mobile networks for them. So all we can do is make sure everything we do on our side minimizes that overhead. So option one is kind of simplistic, but it actually works really well. I just call it the global dump. What we do is we use a single API call that basically downloads everything to the mobile client. Whether this is a JSON dump, an actual SQLite database file, a log of SQL queries, maybe compressed down, you can send down. But what happens is the client will pull it down, create its own version of that database, and then just do a swap. So it'll take the old database, drop it, and pull the new one in. You can do that swap really quickly on both iOS and Android, we found. So it actually, if anything, minimizes data inconsistency. So the big pros of that are it's a single HTTP request. One of the things we had with REST in the beginning is we had orphan data. So if we made a call to update all of our, so we're obviously big in the music, so update all of our artists, and that failed for whatever reason or it didn't complete, it timed out, then we made a call to get all of our songs or content or something that was related to an artist. It could fail because, and actually, invalidate the data because that artist didn't exist. By doing this one big global dump, we download the one single file, we validate it, and then we make the switch. So we can guarantee that the data is where it needs to be. So what are the cons of this? Obviously, it's really simplistic, but when you actually have a lot of different data, so if you have 10,000 artists, if you have 10,000 songs, you'll be bandwidth limited. So that's when the bandwidth actually is worse than the latency in this case. If you do have an application that it does allow users to edit, so obviously for listener, we're not letting them edit artists or edit things like that, but if you did have something where users can make changes, if you sent up a change and then immediately pulled down the database, there's a good chance it's not going to be there. So you could overwrite local changes, and you'd have to be conscious of that. And it's only a read-only call. So it doesn't fix the problem of anytime you want to write data, you still have that overhead of the latency of the mobile networks. Just some general notes. This was actually our first solution at Listener. This is what we ended up with when we finally got off the bus in Austin. We kind of minimized the number of times we called this. By any time you logged in, we'd send down when the global dump was last updated, or when any content was last updated. And if that was later than when we last updated on the client side, then we pulled down. It was an easy win. It was something I could do on a bus. It was something that we actually still use in the current version in the App Store. We just don't have enough content that is a big negative yet. But as we kind of get more into the two-way street, so our users are providing us with more data and more actions, and not just reading from a server anymore, this is not going to be a long-term solution. And some Python-specific notes on how we did it. Just used Django. We did a big class-based view that just pulled down all of the models and parsed one big JSON file. That cache was actually warned by Celery, so Celery would go through, I think, every 60 seconds and rewrite that JSON file, so that if you were the first person to go out and pull that, you wouldn't get hit with that really long load time. That's just something you should be doing for anything in a mobile network. Is a lot of times in websites, you have this idea of a cache, and then after 60 seconds, the next person who comes will regenerate the cache, and then everyone after them will hit it again. With mobile, the whole idea is to minimize that at all costs. So you want to make sure you have some external service, whether that's Celery or a cron job, whose job it is to write to the cache and not from a mobile user. And then one thing I thought was really cool is Django, if you use their database abstraction in ORM, which I don't know why you would be using Django if you didn't, they actually make it really easy to just copy databases and change the format. So you could say, you could have a nice big Postgres table, and you want to make a mobile version that you send down to your mobile clients. You can easily create a new database as SQLite, copy all the models over, and then save it down and send it out. So it was 20 lines of code to create a nice SQLite database. So option number 2 is something called HTTP pipelining. Basically, on the surface, it was made exactly for this situation. The thought process when they designed it was for really high latency networks, and in their head, it was satellite networks. So basically what happens is, on the left, we have normal HTTP. And actually, it's HTTP persistent, because those are 3 calls on one open and close. On the right, though, we have HTTP pipelining. And what happens is it does not wait for the server to respond before it sends the next one. So it just sends them as it has it. The only caveat is the server has to return them in the same exact order. And this can be a real big issue, as we'll see. But in theory, it's something that would basically solve all of our issues and call it a day. It was written as part of HTTP 1.1. It is different than the keep alive persistence that you see everywhere. That is just basically reusing the opened connection and sending those back and forth. But you still only do one at a time. And HTTP pipelining is actually Apple's suggested method of increasing mobile performance through a network. They did a talk in WWDC 2012, basically all about pipelining, how they saw, in some cases 30 to 60% increase in performance. But they, I don't know if they lied about it or they just had a best case scenario. So what are the pros here? Requests are sent without waiting for a response, and theoretically can provide a huge increase in speed. Now, the cons are responses must come in order of the request. So if that first request you send actually takes 2 seconds, even though you sent the other 2 right away, they still have to wait on that first one to return before they can return. Proxies, which are everywhere in a mobile network, will normally negate pipelining entirely, or do worse. What will happen is the proxy won't respect the order because they don't understand pipelining, so they'll send a response out of order, and then your network queue will freak out and then just start the whole thing over again. So even though your server handled it and your client handled it, everything in between wasn't ready for it, and things arrived out of order. And most importantly here is most Python servers just don't support it at all. One thing that's really interesting to me is all these servers would say they're HTTP 1.1 compliant, but they don't support pipelining. It really just means they support persistence. So there's no badge that has everything they support. They just call it 1.1, even though they don't support all the features. So we wanted to test all this because we saw the Apple talk and we thought it can't really be, that crazy. So I did my research, and the longest part of this was finding a Python server which actually supported HTTP pipelining. It was gEvent, and if you look in the bottom right, it's gEvent with PyWSGI. If you don't add that underscore there, it does not support pipelining. So this is one of maybe 3 Python servers that actually supports it, which wasn't a good sign for me. But I decided, you know what, Apple still said it must be right. So we wrote a little view, basically taking a request, sleep for 2 seconds, and return about 1 kilobyte of data. And then we ran on our mobile client, basically just had a flag. On mobile, at least on iOS, it was just a flag of run connection pool or run connection pool with pipelining. And here are the results we got. So we had 40 requests. We averaged out the time it took to complete all 40 requests. And this was on a mobile network reaching out to a server in Tokyo, just to really blow it out to the extreme because we really wanted to see the big increase with pipelining. And obviously, just not there. Not at all. We basically were getting 3,800 milliseconds response time. So 2 of those seconds were just waiting, and then the rest is basically the latency. So what should have been a best case scenario ended up being just disproving it almost entirely. And the reason for that is because of those mobile proxies. When we did a similar test in the office, we could definitely see that it was sending those requests all at once. And what we tried to do was then implement fake latency on a firewall, and it sort of worked, but the numbers really didn't look up. But it didn't matter because in real life, it just, this happened. So, it's just not worth it on a mobile network. Now, if you do Wi-Fi, again, you start to see increases. But, once you get on the mobile side, which is where you need to see these increases, they just aren't there right now. There's a chance that proxies, the latest version of Squid proxy actually supports HTTP pipelining, but what are the chances that's going to make it out to mobile networks in the next 5 years? So, some Python-specific notes. As I talked about, gevent supports pipelining, but only PyWSGI. And then my other note of, they may say, others may support it. I didn't have time to test literally all of them, but I found out that HTTP 1.1 compliant doesn't mean anything. So, and the winner, WebSockets. So I always thought of WebSockets as something people use to make better HTML games or try and make a Google Wave and failed. So, God rest its soul. So we decided to look at WebSockets as a possibility on mobile. Luckily, we weren't the first, so we didn't have to write any libraries. But WebSockets, if you don't know what they are, it's a protocol written over TCP, completely separate from HTTP. But what happens is it starts as an HTTP request. It goes out to the server. If the server says, yes, I like WebSockets, you like WebSockets, let's be friends, it gets upgraded to a full TCP socket connection, and you get all the benefits of just doing raw networking. It has increasing support in a lot of web servers, especially in Python. And the biggest win, I think, is it supports HTTPS. So all the encryption that you're used to on the web, all the encryption that proxies and load balancers are used to, is just a big win right there. And it means you don't have to try and implement it yourself over TCP. The way I kind of like to explain it when I'm talking about our new network stack to my CEO is HTTP is a conversation. I'm talking to you, you tell me, I tell you, you tell me. Sockets is just two people yelling over each other the entire time, which, in real life doesn't work, but in this case, it's perfect because everyone's just saying their mind and it's all perfect. So we wanted to take that same test we did with pipelining and apply it over to WebSockets. So Django has absolutely no support for WebSockets, and anything you tack onto it just wasn't real life. So we decided to go with Tornado. And you can see here, on the on message there in the middle, I would read the message, I would generate a I/O loop to wait for 2 seconds, and then send the data back. So exact same thing, more event-driven than the last one, though gevent was really helpful, the last part. And here are the results. So it took 4.04 seconds, literally the same time it would have taken for one request. It took the same amount for 40 requests. So obviously that would fluctuate a little bit, but clearly it's just going to be the best case for minimizing the amount of traffic if we have a high number of requests. So again, what are the pros? It starts as an HTTP request, which means it will actually follow through the proxies of a mobile network fine and actually get to its destination. It's just now recently supported by Nginx. They will load balance WebSockets for you, which is just a huge win. You get all the socket level benefits of speed and just pure data connections. And again, the standard SSL encryption. So when you want to protect that, again, over a cell network, which is really important to protect that, as what is it, Facebook was sending unencrypted, or LinkedIn or someone. It's really important that you send that encrypted. So having that built in means you don't have to implement it yourself. What are the cons? So what is really happening is you're sending this WebSocket, and then you have an open socket. Well, now you have nothing that looks like REST anymore. You don't have anything that looks like HTTP anymore. You're literally just sending messages back and forth. So you literally have to, at this point, create your own protocol. You would have to say, it could be anything you want. It could be English-based if you really wanted to, but you could say, I could just type artists, and it would just print me out all the artists. It's more like a command line at this point than it is anything else. Again, proxy sucks, so some will actually, it's more of a problem over in Europe, but they will interrupt WebSocket. They'll strip that header out. Two ways around this is use the SSL, which you should be doing anyways, or if you really don't want to do it with encryption, you can just send unencrypted traffic over the port 443, and you get around that entirely. And another con, which is also a pro, but to take full advantage of the WebSocket, you have to be on an event-based server. So if you already have an existing API that you're trying to make better for mobile, this may not be an option because it does require almost a full rewrite. Now, for listener, that was a no-brainer. Our entire business model is based on mobile, so we need to make that as fast as possible. But because of this event-based server, is this comparison really fair to go pipelining versus WebSocket? Not necessarily, but I'm okay with that because it's real life. If HTTP pipelining could have been that godsend, or it looked like in theory, where it's just sending them all at the same time, just receiving them all, then we wouldn't have to rewrite our API. So that should have had much higher returns. But since we're willing to rewrite, I want to rewrite to the fastest thing possible, and that's going to be WebSockets. A next thing is, what I think is actually really cool, is if you like the idea of having a REST framework, so being able to call some domain name /artist /100, if you really like that idea, there is something called WAMP. I have no idea what it stands for right now, but it provides what's called Remote Procedure Call, or RPC, over a WebSocket. So you get these HTTP-like endpoints, but in reality, they're just like an HTTP call, they're just turned into raw messages over a TCP socket. So what that really looks like in your code is, if you're using a raw WebSockets, you set up two functions, your send function and your receive function. And every time you receive something, you'd have to parse out what that means and decide what to do with it. You have to write basically your own router to say, okay, what does this say? Where should I send it? How should I handle this message? With WAMP, you basically can make a very similar call. You can say, make a call over the WebSocket to artist /100, and it's going to give that call an ID. And then your server is going to respond to that ID. So with WAMP, you kind of remove all that routing. It's going to be sent back to that original function as a response. So you can say response equals blah, and it will actually get sent back through that function. So it operates very similar to HTTP in your code, but obviously the backend is completely different. So if you're interested in doing more with WebSockets, what are the best WebSocket libraries out there? From a server standpoint, my favorite is Tornado. Tornado was written originally by the guys at FriendFeed, and then they got bought into Facebook, and they actually still maintain it to this day. Really great event-driven web framework. Just does, it's kind of like the Node.js of Python. Just really, really fast. And when we were doing stress tests with WebSockets, we compared, Node.js along with all these different Python frameworks. Node.js was actually the fastest in terms of number of connections it could handle, but after a certain period of time, the Node.js server would just lag for about 3 seconds and then come back. Second place was Tornado, which was just behind Node.js, and it was consistent for the entire length of our test, which was like 30 minutes. So it was really, really stable, and it's definitely what we're going to be using going forward. There are some just general WebSocket libraries written in Python, if you just search GitHub. They're great just for tacking on to something like Falcon or Flask or something like that if you just want one small piece of your API to be a WebSocket. So if you're just trying to do, like if you're trying to add a chat-based function to your website or something like that, you could do that. And then there's actually a bunch of APIs out there or a bunch of libraries that already integrate WAMP. So if you're not looking to integrate that yourself, one is Autobahn. Autobahn Python is both a WebSocket server written in Twisted. It's a WebSocket client written in Twisted. And they also provide all the client APIs you could ever want. So iOS, Android, JavaScript. And so then you can have that same network stack everywhere that you're writing. One of the things I wanted to touch on, now we talked about all that fun stuff, is keep battery in mind when you're doing this. When you're making these API decisions, obviously we're writing the servers, not the iPhone apps, but if you're relying on a long-standing connection, that's just draining battery. That's all it's doing. So even though there's that overhead of a long latency, you still want to make sure that you're keeping the connection open for really 10 seconds or less. Otherwise, you're just going to have horrible battery life. And even with WebSockets, you still need to continue to leverage the easy wins that I talked about. Caching, throwing things in the Celery, validating on the client side. Because everything comes at a cost on mobile, and the cost is usually really high. So thank you very much, guys. It looked like I ended a little bit early, but so definitely time for questions if anyone has any. If not, I can ramble on more about what we're exactly doing at Listener. So, yeah.
Curious if you looked into doing deltas at all for data to just reduce the number of bytes going over the wire?
Yeah, we, just in terms of pure REST on our global call, we were looking at just sending down what those updates were. Since we were doing JSON for the longest time, there was no easy way to generate that JSON. But when we were doing SQLite once, yeah, we were definitely looking at deltas, but it was just, it was actually pretty difficult to do on mobile compared to what we currently were doing, and it wasn't worth the cost at the time. So that is a good idea. It's another really strong suit. Any other questions? Yeah.
You indicated that Django and TCP was really slow. Can you talk more about that?
Yeah. Yes. So he asked that Django and TCP were actually slow. They're slow in the case of mobile. So there's not so much TCP, and REST framework would have still had the same problem. It was that when you're doing something completely RESTful, you're making a lot of network calls, and so there's no way to do that fast on mobile. All right. Awesome. Well, thank you so much, guys.